one of the most important result in Riemann integration is Riemann's criteria. So in this video, we are going to state and prove Riemann's criteria. So let us look at the statement. Statement says like this: let R be a rectangular region in R. Let f from R to R be a bounded real valued function. Then f is integrable if and only if for every epsilon greater than 0 there exists p epsilon, a partition of R, such that uf p epsilon minus lf p epsilon is less than epsilon. So we'll prove the direct part first. So let epsilon greater than 0 be arbitrary. We want to prove that there exists a partition p epsilon of rectangular domain capital R such that upper sum of f with respect to that partition p epsilon minus lower sum of f with respect to that partition p epsilon is less than epsilon. So what is the given thing? Given f is integrable over R. So that means this implies double integral of f dA over R exists and is equal to uf is equal to LF, where uf is a upper Riemann integral, LF is a lower Riemann integral. As f is integrable over R, these two integrals exist and their value matches, and double integral of f dA over R is equal to common value of these two integrals. Now, by the definition of uf is equal to infimum of ufp such that p is any arbitrary partition of rectangular domain capital R. So what can we say about uf minus epsilon by 2? Sorry, uf plus epsilon by 2, as uf is the infimum of this set, which is a collection of all upper Riemann sums of f with respect to partition p, where p is any arbitrary partition of R. So uf is the infimum of this set. So uf plus epsilon by 2 cannot be a lower bound for the set ufp, where p is arbitrary partition of rectangular domain capital R. So since uf plus epsilon by 2 is not a lower bound for this set, so there exists an element of this set which is less than this. So this implies there exists P1, a partition of R, such that u of f is less than or equal to ufp 1 strictly less than uf plus epsilon by 2. Similarly, by the definition of L of f, we can say that L of f minus epsilon by 2 cannot be upper bound for LFP, where P is partition of R. So by infimum characterization or supremum characterization, we can say there exists P2 partition of R such that L of f is greater than or equal to LFP2, which is strictly greater than L of f minus epsilon by 2. Let us call this statement as statement number 1 and this statement as statement number 2. Let P epsilon be the partition of R which is a common refinement of P1 and P2. So from statement 1 and 2 we have U of f less than or equal to U f P epsilon strictly less than U of f plus epsilon by 2, and L of f greater than or equal to L of f P epsilon strictly greater than L of f minus epsilon by 2. From the above two statement, it is clear that UF minus L of f less than or equal to UF P epsilon minus LF P epsilon strictly less than epsilon. But UF and LF are equal, as the hypothesis says f is double integrable. So this implies 0 less than equal to UF P epsilon minus LF P epsilon strictly less than epsilon. Observe the right hand side. When I subtract LF minus epsilon by 2 from UF plus epsilon by 2 minus plus epsilon by 2 becomes epsilon, and UF minus LF. UF and LF are same, so they will cancel each other. So what left is only epsilon. So we could prove that if f is R integrable, then for every epsilon there exists a partition P epsilon of R such that UF P epsilon minus LF P epsilon is less than epsilon. Now let us prove the converse part. Conversely, we have there exists a partition P epsilon of R such that UF P epsilon minus LF P epsilon is less than epsilon, and the statement is true for any epsilon. The statement is true for any epsilon. We want to prove that f is integrable. So it is that we want to prove that U of f is equal to L of f. Now to achieve this, let epsilon greater than 0 be arbitrary. So by hypothesis, there exists P epsilon, a partition of R such that UF P epsilon minus LF P epsilon is less than epsilon. we know that u of f is less than equal to UFP and L of f is greater than or equal to LFP for any partition P of rectangular domain capital R. So by combining this statement and these two inequalities, we have u of f minus L of f is less than epsilon. But the epsilon that we have chosen was arbitrary. So we get for this epsilon arbitrary, UF minus LF is less than epsilon. So we got that for any epsilon greater than 0, U of f minus L of f is strictly less than epsilon. And we also know that 0 is less than or equal to U of f minus L of f. So overall we have got 0 less than or equal to U of f minus L of f strictly less than epsilon. So this implies U of f is equal to L of f. This implies f is integrable and double integral of f dA over capital R is equal to U of f is equal to L of f. So that proves the converse part. So the statement says R be a rectangular domain in R2, f from R to R be real valued bounded function on rectangular domain capital R, then f is R integrable if and only if for every epsilon greater than 0 there exists a partition P epsilon of R such that UFP epsilon minus LFP epsilon is less than epsilon. That completes the theorem.